Yes, the following calculations can be used to get the current drawn on the single-phase connections. I equals I plus I minus I divided by 2. I equals I plus I minus I divided by 2. I equals I plus I minus I divided by 2, where I, and I are the currents measured at the original three-phase source phases A, B, and C, respectively. These calculations are based on the principle of balanced three-phase systems. In a balanced three-phase system, the currents in the three phases are equal in magnitude and phase shifted by 120 degrees. If the three-phase system is unbalanced, the calculations above will not give accurate results for the current draw on the single-phase connections. However, if the system is balanced, these calculations can be used to determine the current draw on the single-phase connections. To further elaborate, let's delve into the nuances of three-phase power systems and how these calculations are derived. A three-phase system is a type of alternating current electrical power generation, transmission, and distribution. It is the most common method used by electrical grids worldwide to transfer power. In a three-phase system, three conductors carry alternating currents that reach their peak values at different times. These currents are offset by 1/3 of a cycle, or 120 electrical degrees. This offset provides a more consistent and efficient power delivery compared to single-phase power. The advantage of a three-phase system over a single-phase system is that it delivers power more evenly. In a single-phase system, the power delivered pulsates with each cycle, dropping to 0 twice per cycle. In contrast, a three-phase system has a more constant power delivery, reducing vibrations in motors and generators, and allowing for smaller conductors for the same amount of power. Now, let's discuss balanced and unbalanced systems. A balanced three-phase system is one where the magnitudes of the three-phase voltages and currents are equal, and the phase angle between each phase is exactly 120 degrees. This is the ideal scenario, as it ensures that the power is delivered efficiently and evenly. In practice, however, systems are rarely perfectly balanced. An unbalanced system occurs when the magnitudes of the phase voltages or currents are not equal, or the phase angles between them are not exactly 120 degrees. This can be caused by several factors, such as uneven loading on the phases, faults in the system, or differences in impedance between the phases. When a three-phase system is unbalanced, it can lead to several problems, including increased neutral current, voltage imbalances, and increased losses in the system. It can also cause overheating in motors and generators, and can even damage equipment. The calculations provided are based on the assumption that the system is balanced. In a balanced system, the sum of the three-phase currents at any given instant is 0. This is because the currents are equal in magnitude and phase shifted by 120 degrees, so they cancel each other out. However, when the system is unbalanced, this is no longer the case. The sum of the three-phase currents is not 0, and there is a net current flowing in the neutral conductor. This net current can cause problems, as mentioned above. Now, let's go through the derivation of the formulas provided. These formulas are based on the principle of superposition. Superposition states that the response in a linear circuit caused by two or more independent sources is the sum of the responses caused by each source acting alone. In this case, we can consider each of the three-phase currents as an independent source. The current flowing in each of the single-phase connections is the sum of the currents contributed by each of the three phases. For example, the current flowing in the connection between phases A and B, I, is the sum of the current contributed by phase A, I, and the current contributed by phase B, I. However, we need to take into account the phase angle between the currents. In a balanced system, the phase angle between each phase is 120 degrees. Therefore, the current contributed by phase B is phase shifted by 120 degrees with respect to the current contributed by phase A. To account for this phase shift, we can use complex numbers. We can represent each of the phase currents as a complex number, where the magnitude of the complex number is the magnitude of the current, and the angle of the complex number is the phase angle of the current. Then, we can add the complex numbers to find the total current flowing in each of the single-phase connections. However, the formulas provided are a simplified version of this calculation. They assume that the phase angle between the currents is exactly 120 degrees and that the magnitudes of the currents are equal. This is only true in a perfectly balanced system. In an unbalanced system, the phase angles and magnitudes of the currents will be different, and the formulas will not give accurate results. Therefore, it is important to ensure that the system is as balanced as possible before using these formulas. If the system is significantly unbalanced, it may be necessary to use more sophisticated methods to calculate the current draw on the single-phase connections. One method is to use a power analyzer to measure the currents directly. A power analyzer is a device that can measure the voltage, current, and power in an electrical circuit. It can also measure the phase angle between the voltage and current. This information can be used to calculate the current draw on the single-phase connections accurately, even in an unbalanced system. Another method is to use a circuit simulation software. Circuit simulation software allows you to model an electrical circuit and simulate its behavior. You can input the values of the phase voltages and currents, and the software will calculate the current draw on the single-phase connections. This method is more accurate than using the formulas provided, but it requires more effort and expertise. In conclusion, the formulas provided can be used to estimate the current draw on the single-phase connections in a balanced three-phase system. However, they will not give accurate results in an unbalanced system. If the system is significantly unbalanced, it may be necessary to use more sophisticated methods to calculate the current draw on the single-phase connections, such as using a power analyzer or circuit simulation software. Keep in mind that electrical work can be dangerous, and it is important to take appropriate safety precautions. Always energize the circuit before working on it and use appropriate personal protective equipment. If you are not comfortable working with electricity, it is best to hire a qualified electrician. Furthermore, it's important to consider the practical implications of these calculations and their application in real-world scenarios. Let's consider some examples. Imagine a data center where server cabinets are powered by three-phase power. Each cabinet contains multiple servers, and these servers are powered by single-phase power distribution units, or PDUs. The PDU distribute the three-phase power into multiple single-phase circuits to power the individual servers. In this scenario, it's crucial to monitor the current draw on each phase to ensure that the load is balanced and that no phase is overloaded. Overloading a phase can lead to voltage drops, overheating, and potentially equipment failure. The formulas provided can be used to estimate the current draw on the single-phase circuits connected to the PDU. By measuring the currents on the three-phase source and applying the formulas, you can get an idea of how much current each single-phase circuit is drawing. This information can be used to balance the load across the three phases and prevent overloading. However, it's important to remember that the accuracy of these calculations depends on how balanced the system is. If the loads on the single-phase circuits are significantly different, the system will become unbalanced, and the formulas will not give accurate results. In this case, it's necessary to use a power analyzer to measure the currents directly. Another example is in industrial settings where three-phase power is used to power motors and other heavy equipment. Often, these motors are connected to single-phase circuits through transformers. The formulas provided can be used to estimate the current draw on the single-phase circuits connected to the transformers. This information can be used to size the transformers and ensure that they are not overloaded. Again, it's important to consider the balance of the system and use a power analyzer if necessary. In addition to these examples, the formulas can also be used in residential settings where three-phase power is available. For example, some homes may have three-phase power to power appliances such as air conditioners or electric vehicle chargers. The formulas can be used to estimate the current draw on the single-phase circuits connected to these appliances. However, it's important to note that three-phase power is not common in residential settings, and it's usually only found in homes with large electrical loads. In summary, the formulas provided can be a useful tool for estimating the current draw on single-phase circuits connected to a three-phase source. However, it's important to understand the limitations of these formulas and to use them with caution. The accuracy of the calculations depends on how balanced the system is, and it may be necessary to use a power analyzer or circuit simulation software for more accurate results. Always prioritize safety when working with electricity and consult a qualified electrician if you have any doubts or concerns. Moreover, it's important to understand the concept of power factor and its impact on these calculations. Power factor is the ratio of real power to apparent power in an electrical circuit. Real power is the power that is actually used to do work, while apparent power is the product of the voltage and current in the circuit. The power factor is a measure of how efficiently electrical power is being used. A power factor of 1 indicates that all of the power is being used to do work, while a power factor of less than 1 indicates that some of the power is being wasted. In a purely resistive circuit, the voltage and current are in phase and the power factor is 1. However, in circuits with inductive or capacitive loads, the voltage and current are not in phase and the power factor is less than 1. Inductive loads, such as motors and transformers, cause the current to lag behind the voltage, while capacitive loads, such as capacitors and fluorescent lights, cause the current to lead the voltage. A low power factor can cause several problems, including increased current draw, increased losses in the system, and voltage drops. It can also result in penalties from the utility company. The formulas provided assume that the power factor is 1. If the power factor is less than 1, the formulas will not give accurate results. To account for the power factor, you need to multiply the current by the power factor. For example, if the current is 10 amps and the power factor is 0.8, the actual current draw is 10 amps times 0.8, which equals 8 amps. Therefore, it's important to measure the power factor and take it into account when calculating the current draw on the single-phase connections. Power factor correction can be achieved by adding capacitors to the circuit. Capacitors compensate for the inductive loads and bring the power factor closer to 1. Power factor correction can improve the efficiency of the electrical system and reduce the problems associated with low power factor. In addition to power factor, it's also important to consider the harmonic content of the current. Harmonics are multiples of the fundamental frequency of the electrical system. For example, in a 60 Hz system, the harmonics are 120 Hz, 180 Hz, 240 Hz, and so on. Harmonics can be caused by nonlinear loads such as electronic devices, variable frequency drives, and arc furnaces. Harmonics can cause several problems, including overheating of equipment, voltage distortion, and interference with communication systems. They can also cause inaccurate readings on meters and protective relays. The formulas provided do not take into account the harmonic content of the current. If the current contains significant harmonics, the formulas will not give accurate results. To account for the harmonics, you need to use a harmonic analyzer to measure the harmonic content of the current. A harmonic analyzer is a device that can measure the amplitude and phase of each harmonic component of the current. This information can be used to calculate the true root mean square value of the current, which takes into account the harmonics. Harmonic mitigation techniques can be used to reduce the harmonic content of the current. These techniques include using harmonic filters, reactors, and transformers. Harmonic filters are designed to block specific harmonic frequencies. Reactors are used to limit the flow of harmonic currents. Transformers can be designed to minimize the generation of harmonic. In summary, the formulas provided can be a useful tool for estimating the current draw on single-phase circuits connected to a three-phase source. However, it's important to understand the limitations of these formulas and to use them with caution. The accuracy of the calculations depends on how balanced the system is, the power factor, and the harmonic content of the current. It may be necessary to use a power analyzer, circuit simulation software, or a harmonic analyzer for more accurate results. Always prioritize safety when working with electricity and consult a qualified electrician if you have any doubts or concerns. Finally, let's discuss some common mistakes to avoid when working with three-phase power systems. One common mistake is to assume that the system is balanced when it is not. As we have discussed, the formulas provided are only accurate for balanced systems. If the system is imbalanced, the formulas will not give accurate results. It's important to measure the phase voltages and currents to verify that the system is balanced before using the formulas. Another common mistake is to neglect the power factor. As we have discussed, the power factor can have a significant impact on the current draw. It's important to measure the power factor and take it into account when calculating the current draw on the single-phase connections. Another common mistake is to ignore the harmonic content of the current. As we have discussed, harmonics can cause several problems and can lead to inaccurate readings. It's important to measure the harmonic content of the current and take steps to mitigate harmonics if necessary. Another common mistake is to use undersized conductors or protective devices. It's important to size the conductors and protective devices based on the actual current draw, taking into account the power factor and harmonic content. Undersized conductors can overheat and cause a fire, while undersized protective devices may not trip in the event of an overload or fault. Another common mistake is to fail to properly ground the system. Grounding is essential for safety and for preventing electrical shock. It's important to ensure that the system is properly grounded and that all equipment is connected to ground. Another common mistake is to work on live electrical equipment. Working on live electrical equipment is extremely dangerous and can result in serious injury or death. Always to energize the circuit before working on it and use appropriate personal protective equipment. Another common mistake is to fail to follow the relevant electrical codes and standards. Electrical codes and standards are designed to ensure safety and to prevent electrical hazards. It's important to be familiar with the relevant codes and standards and to follow them carefully. In conclusion, working with three-phase power systems can be complex and challenging. It's important to understand the principles of three-phase power, to use the appropriate tools and techniques, and to follow all safety precautions. If you have any doubts or concerns, it's always best to consult a qualified electrician.